Good morning, guys.
Good
Hello.
morning, sir. Good morning, sir.
Just a second. There is something happened to my headset. Yeah. Now is it audible?
Yes, sir.
Yes, sir. Yeah. Fine. Okay. Great. Any doubts so far in the previous day session?
No, sir.
Else we will continue with today's session. Okay. Fine. Okay. Before entering into this, I would like to ask you a simple thing. What is the difference between kinematics as well as dynamics?
Sir, kinematics is the study of the motion without considering any forces, and dynamics is the study of motion considering the forces.
Okay. What will be happen if I will consider the self force, I mean itself force as a load, then it should be dynamic or it should be kinematics. The robot itself is having a weight or the link itself having some weight with it. So if I consider that force, then what it should be?
Kinematics.
Dynamics. The
Kinematics,
dynamics.
sir.
Okay, it is kinematics only. The self load will always be considered as a, even if we consider it as a additional load, but the particle is made with some material, so the material itself is having some weight with it, so we'll call it as a kinematics only. Other than that, additionally we are attaching something, some accessory to it or attachment to it, then we'll call it as a dynamics. Okay, now in this session we are going to discuss about this kinematics occur in the robotics. So which means how the robot is moving. So on what basis we are going to calculate the kinematics? If it is a dynamics, how we are going to differentiate it? And there will be having the classification, how this will be classifying. All these things we will be going to discuss in today's session. Okay, just a second. Let me on my cursor. Okay. I hope you know completely what exactly kinematics is. If a robot is there, this is a simple skeleton, and from this moment, if the robot is moving to this direction, upward direction, this angle 90 degrees, okay, from this, it was reaching to this location. This is called as a kinematics, I will say. The movement of an, okay, how exactly it is moving. So what is the force involved to move it? So what is the final position? To calculate all those things, we will be calling it as a kinematics. If the robot is picking a component or a particle here and it is trying to move to some location, same location like this, then we will call it as a robot dynamics. Okay. In general, we'll use the word robot kinematics itself. In the kinematics itself, it is classified into two things. One is forward kinematics and second one is inverse kinematics. I'll say forward as well as inverse. These both are for calculating the position, I mean calculating the robot movement only. So if a robot is there like this, okay, from this position to this position it has reached here. In both condition the robot is moving to the same condition. Here the robot is, let us say an example, the robot is like this, it is picking a part, okay, not picking a part, the self robot initial programming I have to done. So this is the first position and this is the second position. From the first position to second position, this position is constant, okay, but this classification will be considering on some red things, how to calculate the position, how to calculate the angles if the robot is moving to some direction, so what is the movement it need to do. So to calculate all those things we will be using forward as well as inverse, but the application which is performing is same. See, this is the first position and this second position is not at all changing, the application which is not at all changing. What is changing here? Calculating. So how we are going to calculate it, that will going to change in these two. Now, first one we will be discussing about forward. Okay, in the forward, see, it is called as the angles to positions. What are you? What you are given? The length of each link, the angle of each joint. What you can find? The position of any point, which means, okay, this is the robot and this is the conveyor belt. From this conveyor belt, the material is coming like this, and it will be going to this location. This is the fixed path. Okay, this is the RZ, I'll say, which means the robot zone. In this zone only, the part that is coming here, a part is here, rectangular part. When the part comes to this location, in this region, the robot will go to this location. It tend to pick the component, and in the separate condition, so this is the second conveyor. Now this is the zone. Okay, in this zone the robot need to place the component. This is PI, picking, and this is PL, placing. So this is the operation that robot need to perform, picking a component from this and placing here. Okay, now this is what exactly my application is. Now I will explain you. Just a second, let me on this one. Okay, uh, this is my cursor robot. Okay, this is the gripper. Fine. Now actual home position, so the home position would be like this. Okay, this is the home position. I will say this is the home position. Now from this home position, what is the location? This is RZ, and this will be like a PZ. Now initially, where exactly the robot need to reach? What is the first position that robot need to go? Where exactly the robot need to go in the initial run? This is 1 and this is 2. Clear? See, this is the home position, which means the robot, without having any operation, the robot would be like this. This is the default position or a home position where no part is entering into conveyor or no part is entering into this zone, RZ zone. Okay, once the material is reached this conveyor, starting on this conveyor, then once it is reached this position, this RZ, then what is the first position that robot need to do? What is the first thing that robot will do here?
So it will grab RZ.
Hmm? Move to RZ.
It will grab RZ.
Okay, it will reach to this RZ. Now, how it will be reaching this? How this arm is moving to this location to RZ exactly to pick this part? How it was happened? Okay,
It will incline at an angle.
see, okay, let me give you one more thing. The length of this arm is some 50 centimeters, let us say. Okay, so if the distance between these two is 100 centimeters, is it possible to reach? Now the conveyor and the robot is having 100 centimeters apart, 100 centimeters distance. The length of the robot is 50, and this is a fixed one. I mean the robot envelope should be having 50 centimeters only, 50 centimeters or 100 centimeters dia. Now will it reach the RZ in this condition?
No, sir.
Why
No,
no?
sir.
Why no? Yes, what you said is right, but why? It should be having some explanation, right? So why it is not going to reach this 100 centimeter conveyor?
So the arm will become short because of 50 centimeter margin.
Okay. The length of the arm is 50 centimeters, so it will reach up to 50 centimeters only, but not this RZ. Now, how can we define this conveyor? Okay, we have placed something. Now, this conveyor is also 50 centimeters apart. Now, the robot need to come to this location, pick the part. How it will going to happen? What we need to do as a robotic engineer to pick that part? Okay, see, one more thing. You are the, I mean, you are the creator here, so you have created this complete layout. Now you know what is the distance between these two. The distance between the conveyor and robot is some 40 centimeters. Let us say 40 centimeters. Okay, and at exact 90 degrees of angle, okay, the turning angle at exact 90 degrees, the robot need to come this location and pick the part. Okay, now clear. See, this is a straight conveyor like this. This is a conveyor like this. When the part will be reaching this 90 degrees exactly, so the robot will come to this position and pick it. It will going to pick this from the conveyor. Now I have given the length also. Now the length between these two is 40 centimeters and angle is 90 degrees. Clear? Now will the robot perform the operation? Guys, first of all, is it clear or not? Or I'll explain you again with some other example.
Again. Sure.
Okay, I have erased everything. A simple robot is there. So this is the simple robot. Now there is a table here from the ground. So this is the base and this is the ground. Okay. The robot is fixed with the base here. At the same time, there is a bench or a table that is also there. Now a part is here. Now I have to do this operation. I have to pick this component by using this robot. Now how can I do that? This is part, okay, part P. By I need to pick this one. How can I supposed to do that? Simple thing. How can I supposed to do that? Okay, let us say the robot is having one more axis like this. What happened, guys? Why are you so silent? Now see, the length of the robot is this much. So it will move further up to this extent. And there is one more thing here. Now, see, I hope it's clear. See, this is the robot and link 1, link 2 and link 3. The link will tend to move some other, this direction also. Up to this extent, this is the final extent. Up to this extent, this will go in this direction. Similarly, this also. There is this much of length and up to this extent, the robot will move downward direction. Now, if at all I want to pick this one, how can I supposed to do this? If at all I want to pick this component,
So robot need to move a little bit in right side and then downward.
okay, which link need to move?
Link 2 need to move right.
Okay, link 2 need to move right. Okay, right. Next.
And third downward.
Okay, link 3 in downward direction. Fine. If this is thing. Okay, here what we are doing here, see, the link is moving right direction. So it will be moving. Let me change it. LA. So it is visible. Now this is my arm. Now as I said, link 3 tend to move. So okay, this is now 3 dash and this is 2 dash. Now what happened here? My robot is finally reached the position. Okay? Clear?
Yes, sir.
This is called as a forward kinematics. Where the part is stationary, we are going to calculate the dimensions. We are going to calculate where exactly the part is. Now by using the you will be having a controller with your hand, in your hand. See, just like this one. So you will be having a teach pendant or a simple iPad or a pad like a controller you will be having. So by using this X, Y, Z, alpha, beta and gamma, So you are going to move this robot. So here this is X, Y, Z, or we'll say 1, 2, 3 and 4, 5, 6 like this. So by using this two link, what you have done, you have placed this one, so it will be reaching this position. After that you have done this one, so it was reached this position. So if you have done this one, what is the thing, what is happened, finally you have reached this part P. Okay, now there will be having some things here. Okay, so which means what is the final position? Now initially the robot need to be at 0 0 0. After reaching this point, what is x y z and value, what are the values of x y z? So it's like 0 and it's like 10, it's like -5 or something. Now what are the coordinates of the point? What are the coordinates of this part then? 0, 10,
comma 10, comma -5.
yes, that is what exactly we are going to get here, the position of any point. Which means, so we will be having teach pendant, which means what we are doing here by using the joystick, just like a joystick or just like something. So we are going to that part itself. So if at all I'm considering my hand as a robot and there is a pen that is in the table or something, I want to pick it. Now what I need to do, I need to go forward and I need to go to the downward direction to pick that component. So finally, after picking the part, what is the robot nomenclature? What is the robot structure? What is the values of that robot? That is nothing but position of the point. That is nothing but forward kinematics. Okay, once after reaching the final point, what are the values of the robot or what are the angles of the robot, these two things you know. So now what is the final point values? So for reaching that point, what is the thing you have done? So where exactly the part was placed, what are the dimensions of that part with compared to the robot? That is nothing but forward kinematics. Okay, so where we will be having the lengths and angles, if this is in this position 90 degrees on the plane, so we will be having 0 10 -5 and 0 comma 0 comma 0, that is alpha beta gamma. If this object was at a plane like this, now what happened, will the angle change? Now can a gripper hold like this? So what will happen if a gripper comes like this, will it going to hold?
It will contract.
See here, if the gripper comes, if will the gripper hold this object like this, is it possible?
No, sir.
So for holding this type of component, what I need to do, see, if this is the thing, if this is the part that is placed here, then my robot should supposed to tilt an angle to hold this part. So this is part. So which means what is the angle? Now initially it was 90 degrees. Now what is the angle? So maybe it's a 30, 40 or 45 degrees based upon the angle, based upon this angle. I mean based upon this angle will be different. Now what will be happened here? 0 comma 45 comma 0. Or if the angle that is tilted in this direction also, then based upon that we will be getting things. Okay. So here in the forward kinematics, what you are going to know? So you are going to know the length of the link. I mean, so how much length you are going to move forward to pick that part. How much angle you want to, I mean, you want to move your robot, that also you are you can calculate is, I mean, you are having the details. And finally by using this length as well as angle, you are going to calculate the final position, that is called as a forward kinematics. Clear?
Yes, sir.
See, in the previous example, what we have discussed, there is a robot here, there is a conveyor here. Now, the conveyor length, I mean, the distance between these two is fixed. What is the distance here? 50 centimeters, let us say. The part that is need to be is 50 centimeters. The robot arm itself is having 60 centimeters of length. So, the position, I mean, this position we know, I mean, this one, X, Y, Z, and we know. If there is an angle, I mean, if there this part is at the orientation of this one, rectangular, or it should be like this. Now I need to hold the part like this in the sideway direction. So according to that, my wrist is going to rotate. That is alpha, beta, and gamma. And finally, so I know this length. I know how to hold this component with the angle. Then I will directly go to that position and will pick this part. So for picking that part, so what is the position? So after picking the part, what is the position? What is the final position of that one? that we need to calculate in forward kinematics. Is clear?
Yes, sir.
Yes, sir.
Whereas inverse kinematics is just reversible. See here, in inverse kinematics, what you are given, the length of the each link and position of the point, and what you are going to find, angle. That's it. See, I'll explain you a simple thing. This is my robot. Okay. Okay. Let us assume this is my robot, and here a path that was fixed here. In inverse kinematics, what has done is the length of each link is given, which means the distance between these two. I know distance between these two, x. I know. Now the position. So where exactly this object was placed, that also I know. Which means from the base height, this is some y. From this center, it is x1. Okay. From z, some distance. If there is a z distance also. So we will be knowing x, y, z of workpiece part. At the same time, we will be knowing x, y, z of robot. So by using these two, we are going to calculate the angle. We are going to calculate the angle. That is what inverse kinematics. In forward kinematics, what we are calculating? We are calculating the final position dimensions. Final position, where the final part is at the place, where the part is at the location, where the part dimensions will be calculated in the forward. Whereas in inverse, so for reaching this part, so what is the angle that need to robot adapt? So if here, see in this application, the robot is picking a part here. Now I know this part dimensions. I mean, from the ground, what is the z height? Okay, what is the z orientation with respect to axis? Alpha, beta, gamma, I know. From the base, what is the x? I mean, what is the z? What is the x? What is the y? All these things I know. Now, what I am going to calculate in inverse, I am going to calculate the theta. For picking this part, so what will be happen here? Theta 1. What will be the theta 2? What will be the wrist? 4, I mean theta 3, 4, 5. So all these things we are going to calculate in inverse kinematics. Okay.
Yes, sir.
Simple thing here, in forward kinematics, we are going to calculate the final position. In inverse kinematics, we know everything, we are just calculating the angle. Same application, see here, I am having a teach pendant with me in my hand or a joystick in my hand. I am going to reach that component. I know all the dimensions of the component directly. X is 50 centimeters, directly I can go for x is 50. After that, y is 10 to move 30 degrees. Then I will be giving 30 degrees. After that, the beta will be 22 degrees. So I will rotate the wrist axis 22 degrees, and there will be a roll, pitch, yeah, some degrees. So after iterating all these degrees, that is forward kinematics. If it is inverse kinematics, directly I am reaching that point by using this x, y, z dimensions, and by I'm picking the part. So after picking the part, what will be the angles? What will be the alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6? All those things I am calculating in the inverse kinematics. Whereas in forward kinematics, I am calculating the positions. Okay. In both applications, we are reaching the final part. We are picking the final part. See here, we are picking the final part here. So after picking the part, what is the dimensions of this part? We are calculating here. After picking the part, what is the robotic nomenclature with respect to theta, with respect to angles, that we are going to calculate. Okay. In these two, which one is the best, which one is a useful one, we can't say like that. Why? Because based upon the end application, some applications, what will be happen, the robot, I mean in the running industry, what will be happen, all the things will be having some dimensions, some layouts, everything will be happen, which means a conveyor belt is coming and a robot is stationary here. So this was defined, this was given completely by the layout itself. So we'll be having all the lengths and by using, if at all the position will be calculated, then automatically the angle need to be found by using this inverse kinematics. If the angle is also given, how much of angle with I need to rotate, then I will be calculating with the point, that is forward. So based upon our end application, so we are going to use either forward or inverse. Okay, see, this is a robotic part, that's why I'm just explaining you in outer ways. But as what will be happen for forward kinematics, there will be having some matrices, so with which you are going to calculate. Same with the inverse also, so there will be having some x, y, z and alpha, beta, gamma. There will be 3 by 3 matrix will be there. By using this 3 by 3 matrix, you are going to calculate theoretically if you want, and you can correlate with the actual value with the virtual value. I mean, by using forward kinematics, you have achieved some x1, y1 and z1. You can directly check these values with respect to theoretical. I mean, there is a formula, there is some matrices that will be there. So you, by using that, by calculating that with, and you can correlate it with both, it will be same. Okay, so the robotics, having the robot simulation itself is having forward kinematics and as well as inverse kinematics involved in it, so that for picking apart, for theoretical presentation, for theoretical backup, everything will be visible in the software itself. So further, if at all you want to check directly, you can go and you can check by using the theorems, and you can calculate it with the actual one and do the analysis part. That's up to you. Okay, clear this one?
Yes, sir.
Same thing, if there is a part here, then we'll call it as a robot dynamics, forward, inverse. But we can't call it as a robot dynamics. Generally it is used for the robotic kinematics itself. Why? Because for the initial run, for the part, I mean for picking a part, the robot is moving, that is a, the robot itself is moving, not after picking the part. So the robot itself is having no any part, that is why we'll call it as a kinematics only. Okay, now the robot programming. Okay, one of the important thing and the last thing in this robotic chapter. What happened? Okay, see, the robot programming is basically depends on 4 methods: manual, walkthrough, lead through and offline programming. I will explain you in detail with this one. Manual method. Manual method is like, it is more like a setting mission rather than a programming. It involves setting mission, stops, cams, switches, relays. This is a manual method. Manual method is nothing but, if a robot is there and I want to set the robot, I want to initially run the robot, or I want to define the robot, I want to define the robot for a program. So to check that one, that is called as a manual method, how the robot behavior will be. So where exactly it is going to stop, where exactly it is going to run continuously, if there is a point to point, how the robot behavior will be, so how much load I am going to lift. So all the manual operations that can be done in this manual method. See, it is more like a setting of mission rather than programming. It involves setting mechanical stops, cams, switches, relays and robot control unit used for short work cycle. This is called as a manual method. Second one is a walkthrough method. Walkthrough method is like, if at all I want to perform an operation which is having multiple operations, by this manual method I can do simultaneously 2 operations, which means picking a part from a location and placing. Picking and placing, like the small applications I can run by using manual method, but the application is picking a part and placing it somewhere, and again picking a part some other location and placing in this chamber. Once these two will be done, again picking it somewhere and placing it somewhere. If there is having multiple operations that is performed by a robot, then robot need to identify something, robot need to having some control units. That is done by this walkthrough method. For this method, initially, see, this program manually moves the robot arm hands through sequence of work cycles. Each movement is recorded into control memory and subsequently playback during the production. Here, speed is controlled independently, appropriate the spray painting and arc welding applications. Now here, first application, second application, third application, 3 applications were integrated here. So what happened here is, now I need to define my robot manually initially. So I need to pick a part and I will be reaching to this location and placing here. First operation was done. Again, my robot need to reach the second operation and it will pick a part and it will supposed to place in this location. That is second operation. Once it was done, the robot will go to pick a part from this one and again it will be placing to this location. Same, picking a part and it will reaching this position. 4 operations will be there. Now what happened here, for each and every operation, the robot will control the memory. I mean, the robot will collect the data and it will record on its own. I mean, the control memory. So first operation saved, second operation saved, third operation saved and fourth operation saved. Here all these things you are running manually. I mean, so you will be having teach pendant with you and you are monitoring the programs at what is the behavior. So So what is the first behavior? If at all I run the cycle for 5 different repetitions, what will be the behavior? All these things can be checked in this walkthrough method, which means we are defining the program and we are checking the program, verifying the program. So if at all it needs for 30 cycles, so you are going to check for 30 cycles. Why? Because you don't know where exactly the robot will going to fail, or what will be happen because of the repeatability and accuracy. So whether the repeatability and accuracy are mentioning at 30th point or not, all these things you are checked in by using this walkthrough method. In this walkthrough method, one disadvantage is speed is controlled independently, which means here this speed will be in a controlled manner. In actual cycle, you want to run this with 1 kmph, okay, 1 kmph speed. But here in this walkthrough method, you can't get this 1 kmph. Why? Because so you are at the robot, I mean, so you are just beside the robot and you are checking at each and every point. So at this point, what will be happen? Because of this overspeed or because of some negative thing, maybe it will collide with the human, there will be accident going to happen. That is why in the walkthrough method, speed will always be in a reduced manner. Even though if you give 1 kmph, it will work with 0.1 kmph only. Why? Because the speed is completely independently controlled here. Why? Because we are manually operating here. So we are at the side of the robot, or we are at the front of the robot, or we are at the back of the robot, and we are trying to run the program and we are going to check it. So we are not performing any operation here. We are performing the verifying part. We are checking the verifying part here. That is what exactly this walkthrough method is appropriate for spray painting and welding operations. For welding operation, what we will done? So if there is a limited number of parts, we are going to do it manually. That is why this welding part, this is like this. And one more thing here, there will be a buffers here. I hope you know buffer. What is a buffer? I have explained you in the plant simulation concepts. What are buffers?
Stockpile.
Hmm?
Stockpile of extra resources.
No. See, there is a mission and there is a mission. Here, this mission is having some 2 minutes of processing time, and this mission is having 5 minutes of processing time. Now, what will be happen here? There is a continuous 100 input here. So for every 2 minutes, the part will be produced here, and there is a conveyor here. The conveyor length is having only 50 centimeters. Okay, if I am using conveyor. Now, what will be happen after certain time? After 20 parts, what will be happen to this conveyor?
Parts will accumulate here.
Okay, all the parts will go into accumulate here. So because of this, what will be happen? This machine is going to block, right? Now here, instead of conveyor, I am using a buffer. Buffer is nothing but a bin where the material will be stored. Okay, here I am using a bin and the buffer capacity is like 50 parts. The buffer capacity is 50 parts and it's like a drum. Okay, I will say this as a wire drum. So what will be happen? There will be a rectangular buffer like this. In the rectangular buffer, so all these 100 parts, 50 parts will be stored here. Whenever a part is coming, it will be stored here like this. It will be stored in this order. So whenever this mission was vacant, automatically operator will pick a part and it will be placing in this mission. So that what will be happen? This first mission is not at all, blocking because of this material. At the same time, second mission is also not in the waiting phase. Whenever the part is done, so automatically you will collecting the part from this buffer and it is giving it to the mission. That is what exactly the main application of the buffer. Okay, buffer is generally used for the material storage between missions. Okay, now what will be happen in this walkthrough method? The robot need to pick a material from this buffer and it will place to the another mission. Now if this is application, what will be happen? Continuously the robot is giving material, I mean some mission is giving material to this one. Now the maximum capacity is 30 for this buffer. Now I need to pick a part and place here continuously. Now for this one, I need to check the cycle. I need to check the time. I need to check the speed, how much precisely it is working, how much accurately it is reaching the buffer. At the same time, how much precisely it will reaching the workpiece. All the things I need to check in this walkthrough method. If the program that we are giving, if the program that is running by walkthrough method is perfectly all right, then we will be entering into lead through method. Okay, lead through method will be in a two different cases. Case 1 is like case 1 and case 2. In case 1, what will be happen? The previous program which we have tested in this walkthrough method, that will going automated here. So directly we are going to run a program. In that program, I equal to or n equal to 1000 number of repetitions, and I'll run the program. I'll run the previous walk through method program. So for 1000 number of repetitions, this continuously automatically operated. And here in this program, what is the speed I have given? I have speed equal to 1 kmph. Now the robot will move with respect to 1 kmph only. Why? Because we have given the automated program and we are out from the robot zone. So the robot will tend to, if at all we are running this one, which means what exactly the robot will think, which means there no any human is in and around region of the robot. So the robot can move, I mean, can perform its operation on its own. So with the defined conditions, if the robot is defined for 1 kmph, then the robot will do that operation. If the program is defined 2 kmph, then the robot will move up to 2 kmph. Why? Because we have given the program and we are executing the program in this lead through method. So there will be no any constraints in this one. Completely what we have defined in the program, that can be operated here in this lead through method. That is case 1. In case 2, what will be happen? Sometimes in recent days, what will be happen? There will be having some teach pendants. There will be having some virtual things with which we can directly control the robot. If there is some applicants is there, and I have connected that applicants to my hand, and whatever application I am doing here, that will be done by the robot itself. That is called as a lead through method. That is one of the thing. See, just like example, I am having a controller in my hand, and by the hand I am picking a component, okay, from the table. So automatically this will be scaled to the robot, and robot will also do the same application, and it will try to pick a part in that region. That is called as a lead through method. Sometimes what will be in more advanced conditions, this is called as a lead through method, where by using, see, where we are using teach pendant or power drive to these options. Teach pendant is a device consists of switches, dials, and robot physical components. Each motion is recorded its control memory, and we can populate because of easy convenience. Sometimes what will be happen by using this controller, some will do the programming. By using this manual, I mean extra logics, there will be running this type of motion. This is called as a case 1 and case 2 for this lead through. Generally this will be used in this case 1 only. So whatever the program we have defined, that will be controlled, completely operated by a teach pendant itself in the complete run. So if you are giving 1000 number of cycles, that will be done. If it is a 2 kmph or 5 kmph, that can be done. So all those things, that is possible in this one. Okay. Next one is offline programming. Offline programming is nothing but just like your CNC program. CNC program you can run in 3 different ways. First method is directly you can go to a CNC machine and there will be a controller. In that controller directly you can program it. That is one run. Okay, that is first method. Second method is like manual part programming. You can pick a pen and paper and you can write the program. If it is 1000 lines, you can write a program like this, and you need to give that manually, and you need to instruct all those things to this controller. That is second thing. Third thing is like CAM, where what happened, so you are created a part and you have done the virtual manufacturing. So once you have done the virtual manufacturing in CAM software, so it will be post processed. Post process is nothing but converting the program, converting the virtual manufacturing file into part programming file, G codes and M codes. So I have defined a part like this. This is what exactly I have defined, turning application. So in virtual manufacturing, I have turned this application with some tools and everything. So once it was done perfectly, then I am going to post process, PP, post process. So once after post processing, what will be happen? This file is going to convert into G code and M code. Now I will download this file in a pen drive, and I will be giving it to the CNC machine, CNC controller, and I will run this application. In CNC machine, I will be getting this type of part. That is what exactly this CAM application is, or post process application is. Similarly, robot is also having that type of thing, that is called as offline programming. By using virtual manufacturing softwares like robotic simulation, RobCAD, RobPro, all these softwares, by using all these softwares, you can create any type of program, which means a robot is there. Robot need to pick a part from this, and it will going to place at this location. Again it will come to this location, it will pick a part and it will give to this location. 4 simultaneous operations is there. If a robot is doing four operations simultaneously, 1 2 3 and 4, Now I want to operate it virtually. So in software I'm going to create these applications, and I'm going to test in each and every parameter, like how it was behaving, what is the collision detection, everything I'm going to check in the software. Once it was done perfectly, once it was running without having any collision, without anything, then I'm going to post process it, and I will be getting a code or a data script here. I will collect this data script in a pen drive. Same, the robot is having a controller, so I will be giving that program to the controller. And just like a pen drive, what is happened in the controller, we will be having a menu. In that menu I will be opening into this pen drive section. In that pen drive section there is a program. So for the first program I'm going to test run it. We will call, in technical language we will call it test run or dry run, where what will be happen, this program what we have defined, what we have obtained from the robot, post process robot software, so that will be tested on a without having any tool. It will be testing for the testual base, so that what will be happen, it will be testing the given motion. So if the robot tend to move in this direction, the robot will try to reach every location in a controlled manner. If I have defined some 1 kmph speed here, but it won't follow here in test run, it will be reaching with some 0.1 or 0.05 speed, so that we can detect the motion, we can predict the next motion. So whether it is reaching to any obstacle or not, if there is some obstacle, is the gas cylinder is there, so we haven't observed that in the, I mean we haven't defined that in the software. So because of which in actual what will happen, it is going to collide here. Now instantly I'm going to stop. Why? Because the speed is limited, and each and every parameter the line will be running. It is like 100 lines of program. At each and every line the robot will execute. Once it was done, it will be executing this one. Once it was done, we will going to execute it. We are going to execute the next line. We are going to execute the next line, so that if there is a obstacle here, directly I can stop my program here. So if the z is having some distance, if the cylinder height is some 10 centimeters from ground, the robot is moving from 9 centimeters, then here in this application I'm going to change z from 9 to 15. I will going to modify it, so what will be happen, the robot will going to move from the upward direction, and next will be synchronized automatically. Now I will try it. So if the rest of the program is running perfectly from this test run, then I will be running it in a professional manner, in a lead through method or in a walkthrough method, so that it will check whether it is running perfectly or not after using a tool, or at high speed what exactly its behavior. That is called as a offline programming. By using some virtual softwares, we are going to convert the robotic motion virtually, and we are going to predict, I mean we are going to download some post process file, and by using that file we are going to give that file to the robot controller, and the robot will do the rest of the application. This is one of the most used thing recently. Why? Because any type of complex operation that can be performed in the software easily. So once the complex operation was done, then we will going to post process it, and we are going to go for a test run or a dry run. Once it was running perfectly, then we are going to go it for the manufacturing. So if there will be having some faults that will be find while using this test run, then all the inputs will be collected again by the software engineers, I mean robotic engineers, and they are going to implement in the virtual application, and again they will be doing this post process, and again it will be like a cycle. Clear? Okay, I hope it's clear. Now I'll be entering into next one, applications. While coming into applications, here lot of applications is there: mission loading, pick and place, welding, painting, inspection, assembly. See, one of the important thing, if it is an assembly operation, generally in a running industries or a bigger industries, we will use kara as a one of the important thing. Why? Because kara is having a 3 rotary axis and 1 linear axis, with which what will be happen, this robot will be having multiple advantages for assembly operations, where what will be having parts from different stations will be there. So it will be reaching simultaneously. At the same time, it will be moving in linear direction also, from upward or downward direction. Once it has reached the final position, so the final tool, the linear tool, will going to move in the downward direction. It will pick the component by using the vacuum grippers, like that. So in the assembly operation, generally this kara will be used in most most of the industries. For painting application, they will be using some articulated robots. For welding application, they are going to use a combination of spherical as well as cylindrical. For pick and place application, some industries will use articulated, some industries will use a linear robots. So based upon the end application, each and every industry will tend to use this type of complete missionaries, I mean these type of robots. So based upon the application, see, each and every operation, by using this rrr robot, articulated robot, I can perform any type of application. But what will be happen if I use this rrr for this welding application, or for this inspection application, or for this sample application? The robot application, the robot is capable of doing higher tasks, but I am using it for a limited number of tasks. Because of what will be happen, there will be a resource wastage is there. To eliminate that, so we are going to calculate what is the type of application that we are going to perform. Based upon the application, we are going to choose what type of robot is fixed for this operation. That is what exactly going to happen in the robot selection. Okay, just a second. Okay, now I will be showing you a video in which you will be having clear idea on these applications. Is it visible?
Yes, sir.
Okay, these are some of the applications of this robot. Well, coming to advantages, I hope after seeing this, the robot will be having a number of advantages. So whatever the application will be, that can be done by using this type of robot. See, anything robot and automation can do in many situations: increase profitability, safety, efficiency, quality, and kinds of products. Robot can work in hazardous environment without need of life support, comfort, as well as concern. Robot do not need any environmental comfort such as lighting, air conditioning, ventilation, noise. Robot can work continuously without experiencing fatigue or boredom. Robots have repeatedly precision all the time, unless something happened to them or unless they were wear out. Robots can be much more accurate than humans, trying linear accuracies and a few thousands of inch. Robots and the accidents, all these things will be having some of the, mostly they will be defined for the advantage. I mean, productivity increase only. So whatever the component you are picking, whatever the application which you are performing, finally, so you are going to increase the material handling rate, or we are going to do the operation in a limited time. So if the actual application is taking 5 minutes or 6 minutes, after using a robot, definitely it will try to change it from anywhere from 5 minutes to 4 minutes, 30 seconds, or 4 minutes, 45 seconds. That 15 seconds will play a key role in a continuous industry. That is one of the main advantages. Why? Because these people are using these robots. Okay, now some of the disadvantages when compared to this robotics. See, a robot replace human work, that will be contain economic problems. This is one of the basic problem that we'll be having. So because of the robot, what will be happen from the starting? You are saying that it is a replacement of a human. It will be replacement to the human effort. That is what exactly it is. One of the disadvantages of robot. Second one is robots lack capability of responding in emergencies. These include inappropriate or wrong responses, a lack of decision-making power, loss of power, damage to the robot and other devices, human injuries. These are the one of the common side effects in the robot. So while we are performing the lead through programming, so while performing some lead through programming, what will be happen? Suddenly some human will be entered over there to pick a part, to pick a tool, or pick to some operation. So but in that application, when he have arrived at that location, so maybe the robot will go into that location with respect to the program. At that condition, what will be happen? There will be collision will be there will be accident will be there. So robot can't predict on its own that there will be a human, there will be a something, so we can't go over there. It won't decide on its own. Even though we are given sensors, even though we have given anything, but the sensors will be having some range. When the obstacle comes from having some 10 centimeters or 5 centimeters, then only that sensor will give the alarm to the controller, and instantly it will be going to the emergency stop. The robot will be emergency stopped. This is what exactly happened. But humans can't be like a 5 centimeters or 6 centimeters because of the size of the human. What will be happen? The robot will collide with him. So once after collision, once the accident was done, then the robot will going to stop. This is one of the main defect of this robot in this robotics. Second one is robotics, although superior in certain senses, have limited capabilities in degrees of freedom, dexterity, sensors, vision systems, and real-time responses. So whatever the degrees of freedom will be having, how much precisely it will work, but sometimes what will be having some position, something human will do a better operation when compared to the robot. That is one of the limitation for these robots. Okay. Just have a look on this video. With this video, we are going to end our session. After that, we will be having an exam. I will be sharing you those details. But have a look on this video. So we will be having a clear idea on how these robots as well as this virtual softwares will work in a continuous running industries or in a bigger manufacturing industries. See now, what is this type of application or which type of robot we are going to use for this thing? See here, the robot is doing. See, that's it. That is what exactly the robot application is. Now, in this application, which type of robot is preferable? What is its motion here?
Picking, sir.
Linear.
Okay, so the application is picking, but the type of application the robot is performing is a linear operations only. It is picking a part and is going somewhere and placing over there. So that is what exactly I am saying. Based upon the end application, we are going to define. This application can be done by articulated robot also, but how much it will be going to rotate. But if it is a linear application, based upon the size, it will be like this. Okay, based upon this only, the robot will be classified. That's it, guys. And see, what have you observed in this video? All these things will be done by digital manufacturing softwares, which means first the layout creation can be done by complete plant simulation software, which you are going to learn from the next week. And the next, all these robot applications, all these precise robot applications, special applications can be done by robotic simulation software. And how exactly the automobile or the component is moving from one station to another station, what is the behavior of the station, what is the inputs that need to adapt, how the human is coming and doing this operation, that type of applications can be done by process simulation software. And how the material movement will be done, so how the material is entering into the plant, how the material will be happening at each and every stage, what will be the input, what will be the schedules and planning records, all those things will be done by some pre-actor softwares, and all these things will be integrated by some other software called a team center. See, this is one of the complete database of a industry where we are going to convert our industry into digital platform by using these type of softwares.